In 1983, a Nobel Prize winner, Richard Feynman, was asked by an interviewer to explain magnetic attraction in ordinary terms. What followed was 11 seconds of silence, ending with a profound statement on his understanding of the world. Feynman's answer wasn't an admission of ignorance. He understood magnetic fields deeply. His answer was a philosophical statement, hinting at a lesson he demonstrated 2 decades earlier at Cornell. In a 1964 lecture on advanced electromagnetism at Cornell, Feynman declared a fundamental concept, the visualization of field lines, to be a lie, not just an approximation or simplification. He challenged students on the definition of a field. While they could describe what fields do, mediate interaction and represent forces, they couldn't explain what a field fundamentally is. The problem was that physicists had spent decades perfecting mathematical calculations, causing the map of the physics, the equations, to overshadow the territory or the physical reality. They stopped asking if fields actually exist. Feynman introduced 2 frameworks, one based on E and B fields, and another, the quote, potentials first approach, using A and phi. Both predict the exact same experimental results, raising the question, which one is true? Feynman's answer: physics doesn't decide which is true, it determines which is useful for calculation. He cautioned against confusing the mathematics with what is truly happening in nature. This approach stemmed from a lifelong frustration beginning in 1936. As an MIT undergrad, Feynman was told not to worry about the physics behind quantum operators, just that the math worked. He vowed to prevent this hollow understanding in his own students. The field made a comeback when Feynman introduced retardation. When particle A moves, particle B doesn't respond instantly. This light speed delay requires something to carry the interaction across the gap, a propagating ripple of influence, which looks an awful lot like a field. The core dilemma remains. Framework 1, local fields, assumes fields are fundamental. Framework 2, direct interaction, assumes direct particle interactions are fundamental. Both reproduce all known phenomena and are mathematically consistent. The key is understanding the flawed assumption that nature picks one mathematical description as its operating system. This is likely wrong. Physics is not about discovering the one true description of reality. This represents a paradigm shift. The old way, the discovery paradigm, sought true equations revealing nature's essence. Feynman's way, the modeling paradigm, builds predictive frameworks revealing nature's patterns. Fields are models, not necessarily fundamental constituents. Feynman also taught that visualization isn't understanding. Beautiful animations of electromagnetic waves create an illusion of understanding. Genuine understanding requires confronting what you don't know, not just watching a compelling visual. Feynman's original 11-second silence and statement wasn't ignorance. He was rejecting the premise that explanation means reducing one phenomenon to another. For him, real explanation is building a mathematical framework that successfully predicts and connects observations. Feynman's teaching cultivated the freedom of not knowing, distinguishing between operational knowledge, knowing how to use the theory, and metaphysical knowledge, knowing what fields fundamentally are. Understanding is about mastering predictive models and maintaining humility.